Very impressive. This is beyond the podium, which is good. I don't like standing behind it. And this is one of the celebrity life activities, and there's the banner over there. Whenever you see in the daily program CLA, that's one of these types of activities. They're all free and they're all fun. So today, it says the classical elements fire, and that's really a very short portion of this because fire is so much more interesting. So let's talk about fire. Whenever I give a talk, I always like to start off with something amusing, and I'll have to walk you through this one because it's not quite so obvious. You see it says they're open 24 hours. You'll see that, right? And then down here it says 7 a.m. Monday to Saturday to 11 p.m. So is it open 24 hours? I don't know. This is my introductory slide. I've just played you the video. I don't really want to go through this now. I've got a lot to cover. If something catches your interest, you can ask me later. I'll just point to that one there. Who's retired in this audience? Good. Who's not retired? Oh, there's a couple of hands up there. Oh dear, I do feel sorry for you. Just get on with that and get it over and done with. It's so much fun being retired, as the rest of us will attest to. So it is an ancient element. There were 4 ancient elements in the ancient Greece science, if you like. This was described by Aristotle in his book on generation and corruption. So water, air, fire, and earth, they assumed made up everything. Those were the 4 basic elements. And that lasted for a very long time, actually, a couple of thousand years at least, before we really discovered the periodic table. So fire, here's fire. It's hot and dry. And you can see how the 4 elements here relate to each other. That later got incorporated into early medical practices. They thought that the 4 elements were related to the 4 humours, and if you were sick, then one of the humours had to be adjusted. Hence you had bloodletting or purgatives making you vomit, and there were some really nasty treatments to try and get the humours back into balance. And that's all I'm going to say about the ancient elements. We're going to talk about fire now. So what is fire? This is the fire tetrahedron. You need all 4 things there for fire to continue. It is the rapid oxidation of some kind of material that will combust in a gaseous atmosphere. I say gaseous atmosphere because I know you're probably thinking you need air for this to take place. Well, not always. We'll come up with some examples of that. So if you want to stop this fire, really all you have to do is remove one part of this tetrahedron somewhere. And there's an example of people trying to remove one part of that tetrahedron to try and stop it. It can, of course, be very challenging to stop fires once they get going. So where does fire come from? Well, this is the Greek myth. There's Prometheus. He stole it from the gods, and his penance, of course, was to be chained to a rock and have an eagle eat his liver. Every day and every night he would be cured, and then the next day the eagle would come back and eat his liver again, and this went on through eternity. That was his penance for giving mankind fire. Well, that's not where fire came from, of course. This is one way that the ancients used to do it, of course, striking flint against iron, and here's an example of how that looks.
Then you would blow on it, so you get the flame.
Where you put it?
And you could ignite.
Good man.
That's actually me in a Viking hut striking flint. So here's some other ways of doing it. You can have fire starters. You've got the bow here. There's a fire piston that was invented in 1745. Or you can get fire from a natural phenomenon, meaning lightning. Lightning will come down, it will start a fire. You can then harvest that fire and then try and keep it alive, which is probably what happened in the ancient days before they discovered how to do it. So here we have a lightning strike causing a fire. This is the wood piston that can also start a fire. This is what a match looks like when it burns after the first second. So here's the match, it ignites here. We go all the way down to the wood burning. But of course, you know, if you use matches, they're very suspect to wind and weather conditions. They can, in fact, be put out quite easily. We'll show you that in a minute. So flint I covered. A glass, here's a magnifying glass igniting some paper. The bow, we looked at that. You can use a battery actually if you short circuit it with something conducting. You can actually ignite something. That's a chewing gum wrapper. And most unexpectedly, you can use water to start fire. How do you use water to start fire? You've got to shape it. So here's an example. This is water in a plastic bag. If you shape it into something that's approximately spherical, you can make a lens out of it, and then with that lens, you can ignite something combustible. I couldn't resist showing you this. Obviously the tool of choice if you want to commit arson. No, it's meant for people that like camping. Has anybody ever used those, by the way? Any campers here that have used those things? Evidently not. Does anybody go camping? Couple there, couple there, couple there. Well, now you know about them. Yeah. Arson, of course, this is the criminal use of fire to do something that you shouldn't be doing, and this is an example of a burning. Now, it's easy to identify now these days. We've got experts that can do this. In this particular picture here, this has a classic V shape, showing that the fire started there. Obviously, that's coupled with internal investigation, and you find that the fire was hotter outside than it was inside. So that's an example of a fire that was set outside the house using some kind of accelerants. And all of these things here indicate that maybe arson has been committed, and really the fire investigators are really good at doing this. The Molotov cocktail didn't get its name here where it was first used in the 1930s in the Spanish Civil War. In fact, it got it when the USSR had a dispute with Finland in 1939, and they said to the world they were dropping humanitarian supplies on Finland. In fact, they were dropping incendiary bombs in Finland, and the Finnish gave them the affectionate name of Molotov's picnic baskets and threatened to retaliate with Molotov's cocktails. And they did indeed, and in fact, many more Soviet troops were killed than Finnish troops, but nonetheless, in about 3 months, they were overwhelmed, and that was the end of that. But the name has stuck, and this is Molotov, by the way, in case you wondered who he was. Che Guevara, you've probably heard of him, called them an arm of extraordinary value. There's Che, a couple of pictures. And really all you need is a bottle, a wick, some inflammable material such as petroleum, and a lighter to get it, and there you go. And there's an example of what it will do. Pretty nasty, the Molotov cocktail. I want to digress slightly and talk about that bright thing up in the sky that gives us all of the heat that we're familiar with, which is the sun. It is not on fire. It is not burning in the way that you think of as burning. What is it doing? It's actually a fusion reactor. And this is an example of one of the fusion pathways going on in the sun. The gravity is so strong on the sun that it is bringing hydrogen atoms together. It's banging them against each other with such force that they combine into another element. They combine into helium. And in that process of fusing those atoms together, energy comes out. And part of that energy that comes out is heat, which is why we feel heat from the sun. There are many more types of energy coming from our sun. Light, thank goodness, is also coming from the sun. as is other forms of energy. So the sun is not on fire, it's a fusion reaction. How long will it continue to react, you ask? Well, if you didn't ask, I'm going to tell you anyway. Here we are now, this is the sun, this is in billions of years, it's not actually to scale, but around about this point here, which is a sort of 5 billion years or so from now, it's going to become what's known as a red giant. That's the end of life, part of that main sequence star's cycle. And it will eventually become a planetary nebula, has nothing to do with planets, by the way, and then it will end its life as a white dwarf. This is of concern for those of us that are still here in a few billion years, because here's the sun today, here's Mercury, here's Venus, here's Earth, and this is going to be the size of the red giant. It's going to be very toasty. Enough said. There are 4 states of matter that you may be familiar with: solid, liquid, gas, and plasma. Fire, as we think of it, is not a plasma completely. It is a partial plasma. And you can see in this example here, there's a strong electric field between these 2 plates. There is not a wind blowing that flame. It is an electric field that is moving the flame over in the direction of the electric field. So it is partially a plasma, not completely. What is a plasma? A plasma is the atoms that have lost all the electrons, so it's charged. That's why the electric field can move the flame. And usually, you don't start making a plasma until you get up to about 6,000 to 10,000 degrees C. The picture there is a hydrogen plasma, where all of the electrons have been stripped off the hydrogen. Where do we find plasmas? Just to continue with plasmas, we find them in all these places. So yes, we have plasma on planet Earth, and plasma actually is the most common state of matter, science trivia question, throughout the universe, but we don't find it much on planets. We find it in these places on planets. So every time you see a lightning strike, we've created some plasma through the electricity passing through the atmosphere. It stripped the electrons off. What about fire down below on planet Earth? So this is a cross-section. There's planet Earth, and there's the middle. There's the core, which is extremely hot. What happens as we start to go down from the surface of our planet? These are 2 gold mines in South Africa, and you can see here at the depth of about 4 kilometers down, because they're pretty deep. These are the temperatures of the rock faces, so obviously they have to be cooled greatly for the miners to work down there. So 60 degrees and 66 degrees centigrade, respectively, for those 2 mines. This plot here shows you as you go down into the Earth, and we're going down as far as the inner core here, which is 6,000 kilometers deep, it's warming up. So this is 5,000 degrees centigrade, which is what the temperature of the inner core is. So as we progress down through the mantle, it gets hotter and hotter and hotter and hotter. You see these science fiction programs where we tunnel through the Earth and go through to the other side and there's no heat? Well, there you go, scientific flaw. It's hot down there. How about some history? Well, what's the first wildfire that we know about? Well, obviously we had to have some trees and plants, and they didn't come around till about 420 million years ago. And that's when we started to get wildfires, because, of course, lightning was old, and it will create fires if it strikes on dry plants. And so we have evidence of that taking place. We have those fossils of the chalcolized plants 420 million years ago. We have evidence of cooked food going back almost 2 million years. There's an example. This is a South African cave, which is the earliest evidence we have of human-like creatures using fire. So we and our ancestors have been using fire. We're not necessarily Homo sapiens. Some of the other homos that you've heard about have been using fire. And there's lots of evidence that fire has been used anywhere from 50,000 to 100,000 years ago for various purposes, cooking being one of them. Anybody seen this film, Quest for Fire? Which is basically an idea of how man may have got fire and kept fire and nurtured fire. It's an interesting film, actually. There's no spoken words in this at all, so if you haven't seen it, treat yourself. I quite like this film, Quest for Fire. Now, the candle. I'm going to spend a bit of time on candles because actually they're fascinating, as you'll see as we progress. Probably thinking candles are so mundane. What on earth can be interesting about candles? Well, they've got a long history, over 5,000 years. This picture here is the earliest known beeswax candle that survives, going back to the 6th, 7th century in Germany. The wicked candle, as far as we know, was invented by the Romans just before the beginning of AD, 500 BC there. The reason the question mark is there is we don't know whether the wick candles was invented earlier in the East. We do know about the Roman invention. We do know they were used in Japan and China, but we don't know how long they've been used there. It was originally animal fat, then replaced by beeswax, and you'll notice there, in the early days, China was actually using whale fat for their candles. And the associated smell that went with it couldn't have been very pleasant. Candles were very important. This is the wax candler's coat of arms in London. This is it here. That's their guild house in London, and they've been in existence since 1485. So this was a big deal in those days. Candles were a big deal. You think about it, it was really the only source of light. You didn't walk into your hut and turn on the switch, did you? There wasn't any electricity, it was candles. 1860, Michael Faraday. Is the name Michael Faraday resonating with you? Have you heard of him? A couple of hands going up. A very important figure in science, and indeed his name is used in some of the SI units now. So, 1860, he gave a 6-part lecture, so 6 lectures on candles. Is there enough to give 6 lectures on candles, you say? Well, these are some of the things that he was talking about. This is the cover of the candle. Everything he said, it was actually written down and recorded. So people continue to this day to give this. In fact, the Royal Society in London does this every year for young people at Christmas. It's the Christmas series that's done in London by the Royal Society. So these are the 6 lectures. I'm not going to read through all of those, but you can have a look. So each number there is 1 lecture, and all of those topics then were covered in that lecture. And these lectures would have been about an hour long, so there's a lot to say about them. And these are the other 3 that he talked about. And don't forget, in 1860, the periodic table was very small. It had only been about 100 years since they'd actually got away from the 4 classical elements as being the foundation of everything. It was Lavoisier in France that finally put the final nail in the coffin of the 4 classical elements when he proved that water, which was supposed to be a classical element, was in fact composed of hydrogen and oxygen. So this is relatively breaking science, if you like, when he's talking about oxygen and hydrogen. I want to play you this clip. It is word for word what Faraday said.
I will tell you in 5 lectures the chemical history of a candle. There is not a law under which any part of the universe is governed which does not come into play and is touched upon in the chemistry of a candle. There is no better, there is no more open door by which you can enter into the study of science than by considering the physical phenomena of a candle. I trust, therefore, I shall not disappoint you in choosing this for my subject rather than any newer topic, which could not be better were it even so good. So, now as to the light of the candle. Notice that when the flame runs down the wick to the wax, it gets extinguished, but it goes on burning in the part above. Now, I have no doubt you will ask, how is it that the wax, which will not burn of itself, gets up to the top of the wick where it will burn? We shall presently examine that, but there is a much more wonderful thing about the burning of a candle than this. You have here a solid substance, the fuel, with no vessel to contain it. And how is it that this can get up to the place where the flame is? How is it that this solid gets there, it not being a fluid? Or when it's made a fluid, then how is it that it keeps together? This is a wonderful thing about a candle. You see that a beautiful cup is formed. As the air comes to the candle, it moves upwards by the force of current which the heat of the candle produces. And it so cools all the sides of the wax as to keep the edge much cooler than the part within. The part within melts by the flame that runs down the wick as far as it can go before it's extinguished, but the part on the outside does not melt. The same force of gravity which holds worlds together holds this fluid in a horizontal position, and if the cup be not horizontal, of course the fluid will run away in guttering. You see, therefore, that the cup is formed by this beautifully, regularly ascending current of air playing upon all sides, which keeps the exterior of the candle cool. No fuel would serve for a candle which has not the property of giving this cup.
It's just a pleasure to listen to the way that Faraday spoke, albeit that was done by somebody else. So, we have a candle, there it is, there's the wick, it melts that wax there, the wax travels up the wick, it vaporizes, and it is the vapor that burns, and as you vaporize that wax, you need some heat to do that. It takes energy away, it cools the wick doesn't burn, and that's how the candle continues to burn without destroying the wick. It is the wax vapor that is burning there. When you put it out, of course, you get this smoke, and as I said, that's the reason why you don't expose and lose the wick, because of that cooling process as the wax liquid vaporizes using the latent heat. You're sort of putting energy in to do that, and it cools the wick. Curfew comes from the French, couvre-feu. I probably pronounced that awfully, but anyway, I don't speak French. And that was the time to put out all the fires. And it was adopted into Middle English as curfew, and now this is the modern spelling, curfew. Well, that's a sign I saw somewhere where we were walking around and took a picture of it. William the Conqueror actually instituted that in England after he conquered England, and all these fires had to be put out by 8 o'clock at night, and so it was pretty gloomy in England. If you've ever been there in the winter, long nights, it would have been nice to have a fire. They tried to preserve them, of course, because you have to cook them. Fortunately, Henry I was civilized, and he repealed that law in 1100. This hut here, you see, round, thought to be the earliest dwelling shape. The reason the door is there in one place is thought to be that they would try and preserve the fire outside rather than inside, and that might have been the reason for a round house. And of course, smoke would have come up through there somewhere, or maybe not come out at all until they figured that out. Chimneys didn't come around until a bit later. This is the earliest extant example of a chimney in England. It's Conisburgh Castle, and it has a relationship to Ivanhoe, but this is the earliest example of chimneys that exist in a castle in England. That's the keep. The Romans, of course, used chimneys. They had invented them. Basically, these were just holes in the wall in the early days until they figured out that they could actually build proper chimneys over fires. And we didn't start getting them in Europe in dwellings there till the 12th century. Common London scene, lots of them. Again, not common until much later in dwelling houses, so 16th and 17th century. And of course, when the Industrial Revolution came along, lots of chimneys for burning all of those things for those satanic mills up on the hill where all the people were working. This is what they were first built of. Yes, you're thinking to yourself, a chimney built of wood, how can that be? Well, obviously the outside of the wood chars and it protects it somewhat, but they certainly weren't built of stone in the early days. That was expensive. What do we use it for? We use fire for all kinds of things. I've listed a few here, and we'll look at a few more. And I'm sure you could think of these. In fact, maybe you could even think of more. So cooking, hunting, creating charcoal to use as a fuel later, because that's a good fuel in itself. Torture and execution, as shown here, where they're executing people for their beliefs. And also in warfare, an example there. We'll come back to that one. That's charcoal. Here's some other uses. Internal combustion. Who drives a car? You're using fire to do it inside the cylinder because you're burning the gasoline. We use it in trades, of course, in wood and metal, in manipulating them. We use it in heating. We use it in lighting. Well, maybe not so much today, but they certainly was used in heating and lighting, and it can even be used in the medical profession for cauterizing wounds. No, thank you, but there you can. Communications, we've used fire in communications, signal fires. When something of great importance is happening, we burn the bonfire, the next bonfire ignites, and then so on, all down the line, so that a signal can be passed very quickly. We can use it in landscaping. We're clearing land here. I actually managed to clear some land around my own house by mistake. Yeah, that was no fun. And we use it for ceremonial purposes here, the fire. This is one of the Olympics, and there's a fire of remembrance. That's a signal tower where a bonfire would be on top. We use it as fuel. Fire is used as a heating from wood, and the fossil fuels that we're using still today, petroleum, natural gas, and coal. This is 2001, but it gives you a breakdown, and it hasn't changed a great deal. So this is oil, this is coal, and this is natural gas. So we use those for generating electricity and other purposes. Flames. Not all flames are equal. So this is the hottest flame that we can generate. It's an oxyhydrogen flame. That will take you up to 2,000 degrees. Then there's a Bunsen burner, which is shown here. Anybody used a Bunsen burner? Yeah, some of you have had science classes. Very good. Well, that's what they can get up to. I can remember melting copper with those. There's a blowtorch. I've got one at home. Candles, of course, will get up to about 1,000 degrees. And cigarettes, if anybody still smokes, you can get anywhere from 400 to 700 degrees in that little flame at the end there. It varies. So, color will tell you something about temperature. So I've given you both the centigrade and Fahrenheit conversions here so you can see. So as we start heating some material up, it will become redder and redder, then it'll become more orange, and then finally, if you continue to heat it up, it becomes what we term white hot. You see the different parts of the flame here, different temperatures in different parts of the flame, depending on the color. Here's some more flames with their associated temperatures. So here we've got an orange flame, a deep orange flame, and then we've got some white here, and as it becomes brighter and brighter, it becomes hotter and hotter. I did say that combusting something in a gaseous environment will give rise to fire, and I excluded air at that point because there are other gases that will support combustion. Usually it's air, usually it's oxygen. You've got to have oxygen for a flame, but this is an example where you don't. This is hydrogen burning in chlorine, which is why it's green. So this is the flame here. It's actually burning in chlorine, and the product there, unlike hydrogen burning in oxygen where you get water as the final product, in this case you're getting hydrochloric acid as the final product. How fast do they move? Well, this is an approximation for the maximum fire speed. It's anywhere from 16 to 20 kilometers an hour under sort of standard conditions. That's certainly faster than I can move. But there's anecdotal evidence that you can go up to 70 kilometers per hour. Now, this really does depend on environmental conditions. Which way is the wind blowing, what the landscaping is, what the fuel type is, what kind of moisture is on the ground or in the material. So under good conditions, if you've got a fire approaching a slope here, this is a 20-degree slope, it will double for every 10 degrees, so it becomes 400 meters per hour going up the slope. And conversely, if it's going down a slope, it's the reverse. It slows down. Same way, for every 10 degrees, it slows down by a factor of 200 meters per hour this way, and then it slows down to 25 meters per hour that way. So what do you do if you see a fire coming towards you? You don't run for the high ground. Run for the low ground. Try and find a river. That would be the best. But even if you get across the river, depending on that fire, maybe it's going to follow you, because fire can jump. How can fire jump? Well, the obvious one is some embers will cross over the river and will ignite something dry on the other side. But if the fire is really hot, then it is the radiant heat coming from the fire which can travel as far as 10 meters, which is 30 feet, and ignite material just from the radiant heat. So it's a 1 over r squared, meaning it drops off with the square of the distance from the origin. So 1 over r squared, the further away you get from it, the faster the radiant heat is going to drop. But yes, it can ignite something. So there's a fire there, and it's going to ignite this tree and eventually that house, simply from the radiant heat. The embers won't get there. Firefighting, well, water still works, thank goodness. That's great. But we have new substances today. They burn hotter, and they can give rise to some very nasty byproducts. So we get, obviously, carbon monoxide and carbon dioxide. But from some of the modern materials, we can get hydrochloric acid, cyanide. This is nitrous oxide, and that's another form of nitrous oxide. So you really do need, the firefighters really do need some protection when they go in. They're using new equipment today. They can use drones to map out fire. They're not putting out fires with drones, but they're mapping it. Drones aren't big enough for that yet. We've got technology that can monitor the location and the health of the people that are fighting the fires. This is really good technology. We're looking at their pulse rate, we're looking at their respiratory rate, all kinds of good information, and also where they are. This is a relatively new development. This is called the Scott site. It's a thermal imaging system, which is shown here in this animation, and that is basically allowing them to see through smoke and also identify which areas of the fire are really very hot. Maybe they shouldn't be going in that area. Maybe they should be trying to find another way around if they're trying to get to a particular place in a house. Fire-resistant materials, here's an example of tantalum carbide. It's being heated here by the blowtorch, and as you can see, it's making absolutely no impact on it. It's just warming up that place where where the fire is impinging. When you take that fire away, nothing's going to happen. It melts at a very high temperature, and so you need an intense fire to get rid of it. Firefighters themselves have some pretty amazing equipment today. So this is the temperatures they can withstand using their clothing. So 370 degrees centigrade they can withstand very briefly. Skin instantly burns at 55. So they can go places that you can't go, obviously. So leave it to the professionals. Don't run into that house. Let them do that. Chemical fires can take place where you absolutely need no gas whatsoever, because the chemical reaction itself gives the gas to support the combustion. And here's a few examples. Sodium chlorate with sugar and sulfuric acid, that will generate its own environment to burn. This is ammonium nitrate powder, zinc powder, and hydrochloric acid. This is potassium permanganate, glycerine, and a little bit of water. And they will give you fires that look a bit like that. These are the reactions that take place in a complete combustion. We will get just carbon dioxide and water from a fire if we're burning, say, methane. But if we have an incomplete combustion, which is the thing that sometimes we do because there's just not enough oxygen around, we're going to generate carbon monoxide and carbon dioxide, in addition to water and maybe some carbon soot. And if we're burning air, this is with oxygen. If we're burning air, obviously we'll have nitrogen left over, because nitrogen doesn't burn. So those are the basic reactions. Now some famous fires. Well, we've all heard of this one, Rome burning, right? It burned for a week. It destroyed 3 of the 14 districts, and it severely damaged 7 of them, and it really damaged Rome a great deal. And we've all heard the story of Nero fiddling, right? Right? It's wrong. He wasn't there. He was in Antium, as written by Tacitus, and he's a fairly reliable historian, so probably worth believing. That being said, though, what happened after the fire? Well, Nero was pretty upset, and he decided to blame the Christians. And these are Nero's torches. So here's Nero over here, having a good time, watching these poor devils here being basically incinerated. Nero's torches. Yes, the poor Christians got. All right, this is Tokyo, 1923. There was an earthquake at noon. There was a firestorm then that came from this. About 30,000 people died just from the fumes. It really destroyed a great deal of the surrounding area. As you can see, 80% of Yokohama and a great deal of Tokyo was destroyed. Almost 2 million homes were destroyed. The death toll, 142,000. It's a bit uncertain, not completely sure how many died, but lots of people did die. And yes, after that, of course, they rebuilt Tokyo just in time for the B-29s to come along in World War II and wipe it all out again. Remember this? I was in Disney World when this happened. I remember looking up at the sky and seeing this. I didn't know what it was until we got back to the motel. And yes, there was a fuel leak. The fuel caught fire, and then the fire resulted in the explosion which destroyed the space shuttle in 1986. Flamethrower, I said I'd come back to warfare. This is an early one, goes back as far as 450 BC, Greek fire, where they were using it from ship to ship. Must have been pretty hazardous. We don't like open flames on ships, especially ones made of wood. This is a modern flamethrower today. I personally would be terrified to carry one of these. A stray bullet, boom, no thank you. Brave guys. Firestorms, this is where the fire is so intense, it creates a big updraft, pulling air in, giving more fuel, and it just exacerbates the whole problem. So this is an example of a firestorm, a natural firestorm over there, and this is how it works. And you get this classic cloud that you see over on the left, and that's shown there in the diagram. And firestorms, they've happened too. This is 1945, this is Dresden. Terrible loss of life, huge area was destroyed, basically from the firestorm. Dresden was firebombed, as I'm sure many of you know. This was a natural firestorm that took place here in the USA, Wisconsin, 1871. As you can see, over 1 million acres, up to a couple of thousand people died in this. The range of people who died in this is a little bit uncertain, but you know, leave it to the military. They studied how this firestorm worked so they could try and recreate it in war. And looking at Dresden, they were successful. Firebombing, of course, we invented napalm and then we started dropping it on people. And this is an example of firebombing. And then this is firebombing from the other point of view. This is where we're now trying to put out the fire by bombing it. In this case, we're bombing it with water, or in this case, we're bombing it with chemicals. And the amount that these planes can take varies depending on what it is. Of course, this is up to, that's the maximum one can take. So almost 20,000 gallons, or 74,000 liters. When we burn something, one of the byproducts is carbon dioxide. I just want to dwell a little bit on carbon dioxide because it's kind of important today. So as we burn, we make carbon dioxide. And it is, of course, as you know, one of the greenhouse gases. It is not the most important greenhouse gas in terms of its effectiveness, but it is certainly one of the most prolific greenhouse gases. That being said, we should be a little bit grateful for greenhouse gases, because if we didn't have any, this is what planet Earth would look like. We would be on an ice ball. So if there were no greenhouse gases whatsoever, the surface temperature, the average surface temperature of planet Earth would be around minus 18 degrees centigrade or 0 degrees Fahrenheit. So really maybe it's good we've got some greenhouse gases, but we don't want too many, of course, because that leads to other problems. But that's another talk for another time. These are surface temperatures that are taking place now, going back here to 1880. This is projected up to, well, actually it's today. So these are different studies showing how surface temperatures are rising. Those are the 5 studies that are showing that. And yes, things are getting warmer. I'm sure you all know that. Where's that extra heat going? Mostly it's going into the oceans. And there is an effect of putting all that energy into the oceans. You may have noticed that storms coming from the oceans are getting a little bit more intense than they were before. And that is because they're getting their energy from the energy that's stored in the oceans. And there's a lot of it's there. Most of the energy is going in there. That's also one of the reasons why the ocean levels are rising. About half of the rise that you hear about in sea level today is due to this heat going into the oceans, expanding water. Wildfires, twice the area burned now in USA compared with 1970. Wildfires are becoming more common. The season has got longer. The frequency has increased. And this is the amount of money that was spent in 2017. That's $3 billion in fire suppression. So just trying to prevent it is very expensive. When we go to Europe, they think they're going to have more problems in the coming years. They're expecting more. They're expecting the burnt area to double. And so where you see in these diagrams here, the more red, obviously, the worse it is. That's going back to the 1980s. That's the early 2000s. And so things are getting worse in Europe too. And that brings me to the end of talking about fire. Thank you very much. I have 3 minutes left. If there's one question, I'm happy to do it from the... That went up fast. If there's one question...